Alright, today I'm going to talk about the physics of how we go from this to this. Alright, here's a pickup. It's like a microphone for the strings. And here's my attempt at drawing one. Alright, so let's check out one of these pole pieces, which are essentially little magnets, and let's look at its side on. So here's the pole piece, it's a magnet, and here's the string. Imagine the string as coming up towards you. Alright, so both of these are made of ferromagnetic materials, so the string consequently will be magnetized, something like this. Because the string is magnetized, it will have its own magnetic field lines, and it might look something like this. Alright, something like that. Before we continue with the model over here, we have to understand something called magnetic flux. Magnetic flux is essentially a measurement of how many field lines are going through a given area. It's represented by the Greek letter phi, and here's the equation. So let's draw a quick little model to understand it. Alright, here's a magnet, and here's our field line. So if we take a given area, for example right here, and remember this is all in three-dimensional space, so these lines are perpendicular to the surface of this area. It has an area A, and the strength of the magnetic field in this given area is B, right? So the flux will be equal to B times A. If we take an area, the same area over here, we know that the strength of the magnetic field will be less, even though the area is the same. Thus, this flux will be less than that flux. Flux can be changed by either changing the given surface or by changing the magnetic field, which is easiest to do by changing the distance. Alright, if we go back to our model, the pickup and the string, just remember that the magnetic field of the pickup doesn't matter. We only care about the magnetic field of the string. So what happens when we hit the string? The string is going to oscillate up and down. It's going to vibrate at whatever the frequency of the note played is. And as it does that, it's going to change the distance between it and the area where this little wire is wrapped around. In doing so, there will be a change of magnetic field in this area. If we know there's a change in magnetic field strength, there will be a change in flux. What happens when there's a change in flux? There's a process called electromagnetic induction. Here's a demonstration. This is essentially the opposite of how an electromagnet works. We are creating electricity by changing the magnetic field. As the string oscillates back and forth, there is a change in magnetic field where the coil is wrapped around. In turn, there is a current that flows back and forth from the amplifier. Faraday quantified electromagnetic induction in his equation here. He said that there will be a voltage induced that is equal to the negative number of times this coil is wrapped times the change in flux divided by change in time. There's a calculus version of this, which if we take the derivative of this, we can get instantaneous voltage. If we graph the voltage induced, we'll get a graph something like this. It'll be sinusoidal. It'll vary as the string moves up and down. The frequency of the voltage induced will be equal to the frequency of our note that we played, which will also be equal to the frequency of the current. We now have an alternating current with the same frequency as that initial note we plucked, which we can send to be amplified. I wanted to demonstrate how simple a pickup really is, so I decided to make one myself. I have a magnet and I'm wrapping it a bunch of times with this wire. Probably got like 300 wraps or something with it. So the magnet is only there to magnetize the string. And if I connect the wires to the 1/4 inch cable which I send to the amplifier, it should work. Well, you know, it does. From this guitar, we send a alternating current. The current flows both directions. Also has an alternating voltage, right? It's poled one direction, then it's poled one direction at this frequency that the note is. Nowhere near as powerful as it needs to be to really move that speaker cone and get a loud sound. Therefore, it needs to be amplified, and we will do that using a vacuum tube. Here's how a tube appears on electrical diagrams, which I'm going to use to explain how it works. All right, so here we have what's called the cathode. And the cathode is essentially a nickel tube coated with metal oxides. At the top we have the anode, or sometimes called the plate, which is really just a metal plate that has a positive charge on it. Here at the bottom we have the heating filament, which through 6 to 12 volts of AC essentially brings the cathode up to about 1,000 degrees Celsius. And in doing so, a process called thermionic emission will occur. Essentially, the electrons in the metal oxides will have so much thermal energy, so much kinetic energy, that they will essentially boil off the cathode, and they will all go shooting up into this vacuum, right? This is a vacuum tube, and it's a vacuum tube which allows these electrons not to be obstructed in their path up to the anode. There is a potential difference of anywhere from 150 to 250 volts between these two, depending on the type of tube we're using. So these electrons are really attracted to that anode. We can control this flow of electrons using what's called a grid. If we charge it positively, the electrons will be attracted to it, they'll be pushed through to the anode. However, if it's charged negatively, they'll be repelled, they'll be pushed back down to the cathode. In a way, this grid is kind of like a electron gate. It opens and closes. We control this grid using the current that we send from the guitar. Quick note about conventional current flow. The way we normally think about how current flows is from positive to negative, right? So when there's a potential difference, we normally talk about current flowing from high to low. However, in reality, that's not the case. So Benjamin Franklin essentially established this way of thinking, and he had a 50-50 chance of getting it right, but he actually got it wrong. In reality, what's actually happening is the electrons are moving, right? The electrons have a negative charge. So it doesn't make any sense for electrons to move from positive to negative, considering they are repelled by negative charges. So in reality, they do move from negative to positive. So when we're talking about the tube, it's going to make a lot more sense thinking about it in reality rather than the conventional current. So when we say there's a higher voltage, there will be less electrons. When there's a lower voltage, there will be more electrons. All right, so when there's a positive voltage, the electrons will be pushed through. When there's a negative, they'll be pushed back. Now, if we graph the flow of electrons, we graph this current that the anode receives. Here's maybe what the direct current would look like without a grid or without any manipulation from a current. However, if we take into account the current flowing from the guitar, we might get something that looks like this. It'll start in the middle. However, as the voltage increases, the current also increases. It comes back down, voltage goes negative, other direction, then the current will decrease. Right? However, there'll always be some that make it through. So you get something that looks a little bit like this. Now, this is not an alternating current, although it may look like it, because for it to be an alternating current, it would have to switch directions. In actuality, this is called a varying direct current. And later on, through a transformer or a capacitor, it will be turned into a true alternating current. All right, so one important thing to notice is that the frequency of the current from the guitar will be equal to the frequency of this varying direct current. The only thing that changes is the amplitude. The amplitude of the guitar signal will be way less than the amplitude of this varying direct current. It is through this process that we essentially enlarge the amplitude, we enlarge the signal from the guitar, and then we can send that to the speaker to vibrate the speaker cone and make a loud sound. Now the amplitude of the signal is large enough to actually do something with the speaker. Here we have the most important parts of the speaker. A permanent magnet, what's called the voice coil, which is essentially a metal wire that's wrapped around the magnet and connected to the speaker cone. Now what happens next is a product of these two ideas. The first one, that when we have a current flowing through a wire near a magnet, there will be a force exerted on that wire that is equal to the current times the length of the wire times the magnetic field strength. Our right-hand rule tells us what direction that force will be in. So remember that this voice coil is connected to that signal that current, that alternating current that we send from the tube. All right, let's say that as the current is positive, it's moving this direction. Let's say that it goes around like that. So it goes in over here and it comes out over here. Represent that using X's and dots. Imagine the arrow of a bow and arrow. This is the tail end, right? It has those feathers, and here is the pointy end. Now we can use our right-hand rule to figure out which direction that voice coil will move. All right, we know that our magnetic field lines go from north to south. So magnetic field goes that way. We know that the current goes downwards. Therefore, our speaker cone will be pushed forward. Same thing on the other side. As the current switches the direction in which it is flowing, the opposite effect will happen. It will switch. I'll be coming out over here and be going in over there. I'll be going like that. As a result of this, the speaker cone will move the other direction. Now, imagine this cone is just a flat sort of plate. As it moves forward, it'll compress all of the little air molecules. All the air molecules around will be compressed in this little area. And we call that a compression. However, as the speaker cone moves back, it creates this area of low pressure, of less air molecules, and we call that a rarefaction. Now, because the speaker cone is alternating between the two, we essentially get alternating compression and rarefactions. The best way to think of it is to imagine this like a slinky being bunched together over here, but then it gets further away, right? These are the compressions, rarefaction, high pressure, low pressure, high, low, high, right? But that's what happens with the air, and we call that a longitudinal wave. And so these areas of high and low pressure, they travel outward from the speaker, and that is what we perceive as sound. These areas of high and low pressure hit your really sensitive ear, and then as your ear senses it being pushed back and forth, it sends signals to your brain to perceive this as sound.